All right, everyone. Let's begin our next unit, which is sinusoidal functions. Sinusoidal functions are going to be somewhat of a review for you. You would have been introduced to them last year, and we're going to go back over it this year and hopefully brush up on a lot of your skills and really focus on the word problems and being able to answer some of the word problems that will be at the end of this unit. But before we get there, I'm just going to quickly introduce what we're going to be going through in this unit. So the first thing is obviously we're going to be introducing what a sinusoidal function even is, or what a sinusoidal or periodic function is. So we're going to be looking at two different types of graphs where they're going to be specifically sinusoidal versus something that is just periodic. So I'm going to explain what that is. And that's how we're going to start things off. We're going to be able to graph sinusoidal functions. Okay, that's going to be a big one. That's going to take up a few lessons, actually, 3 in total. So we're going to be able to graph sinusoidal functions. And that is, of course, the equations and the variations of the equations of y equals sine x and y equals cos x. Okay, so these are also functions as part of our course, and you'll see why they're functions and why they fall in the category of functions and what their graphs look like. And we'll be able to graph the different variations of these. So we're going to be eventually stretching, compressing, reflecting. There's going to be phase shift left and right, vertical shift up and down. We'll be able to handle any sort of sinusoidal function equation and be able to graph it. Okay, we're going to look at real life applications, and there's a lot of them that follow sinusoidal curves. Okay, so there's a lot of situations in real life where you can apply a sinusoidal model in order to make predictions, whether it is predictions within your data or predictions outside of your data. You can do so. So for example, if I were to plot, let's say, the day of the year on my x-axis and the temperature. Now I'm going to stay above 0 here, so I'm going to assume that we have, let's just pretend for a second that we are in a warm climate and the temperatures stay above 0. Imagine a scatter plot that plotted the temperature and the day of the year, right? And so let's say this was day 1 or day 0. I assume we can start at January 1st, right? So this would be like January 1st, all right? And actually, we'd probably start that as a 1 and not as a 0. Okay, so we'd start at January 1st. And the temperature would probably be pretty cold, so it'd be low. It'd be cooler anyways. And as the days wore on, and I mean, this will kind of, it's a scatter plot, right? So it's going to kind of be all over the place. But as the days wear on throughout the year, you're going to see that the temperature, say, increases, right? And then it reaches its peak, let's say at some point in late July or of some sort, and it starts to dip back down. Okay, remember, this is just a scatter plot. It starts to dip back down and eventually go back to roughly where the January 1st temperature was. And maybe I'll erase these points. Okay, so and think of this now if you continued for multiple years, right? So imagine for multiple years you were plotting temperature, getting data for it, right? And so what you would find is that temperature, I'm just doing this quick here, is cyclical, all right? It is cyclical. And if you were to look at what the graph of y equals sine x or y equals cos x looks like, it would fit this data, this periodic or cyclical data, okay? And so that's important. So based on our history, right, if we were to plot all the way back from when we started recording temperatures, let's just call it in the early 1900s, okay? And we were to plot all the data, we would see probably as each year goes by, we would just kind of see this up and down, up and down, up and down, up and down cyclical effect each year, where the temperatures, of course, aren't the same each year. For like January 1st, temperature won't be the same for every January 1st, but it'll be roughly in a certain specific area, right? So maybe it's not minus 20 one year, or maybe it's minus 20 one year, the next year might be minus 22, but nevertheless, it's still within that area. And from that, you can model it with potentially a sinusoidal or a sinusoidal curve, and then eventually make predictions into the future. Okay, so that's just one simple example of a cyclical pattern that can be modeled using a sinusoidal function. All right, so that's just my brief introduction there. Let's get into, there's a lot we obviously need to go over. And by the way, if I were to just list off some of the other applications of sinusoidal functions, I mean, they occur in radio waves. They occur, obviously, radio waves are sound waves, electrical currents, tides of water. Okay, there are so many examples. And on my website, actually, if you go to my website, I actually give a few more examples as well for this opening lesson of just some applications of sinusoidal functions. Okay, but let's dive into our first lesson, all right, which is a simple investigation. We're going to go over some definitions here, and by the end of it, we are going to know what the graphs of y equals sine x and y equals cos x looks like, and we'll know what the table of values will be that will produce these curves. Okay, so we're going to look at coming up with a table of values that will create the graphs of y equals sine x and cos x. Along the way, we're going to learn some really important properties that deal with sinusoidal functions, and you can see that we're going to start with definitions. Okay, so let's start there. So again, what you want to take from this lesson is you want to be able to define and understand these terms that we're going to be going through. That's going to be a big thing. You're going to want to be able to create a table of values for the equation y equals sine x, as well as for the equation y equals cos x, and then plot their graphs. Okay, so that's what we want to take from this. I mean, we want to build towards getting to the applications of this, but we can't do that until we understand the ins and outs of the functions themselves. Okay, so let's begin with some definitions. So let's start with what's known as a periodic function. Okay, a periodic function is a relationship between x and y variables that follows any sort of cyclical pattern. Any sort of cyclical pattern. Okay, so it could be any sort of graph that follows a cyclical pattern. So imagine something that looks like this. Maybe like a bunch of, if you were to plot all the data and you were to draw a curve of best fit through it all, you would find that it creates like these little triangles, or it could be any shape, right? It could be, it goes up, goes flat, goes back down, goes up, goes flat, goes back down. These are all periodic functions. They occur over and over again. The same shape continuously occurs. That's different, slightly different than sinusoidal functions. So sinusoidal functions are a type of periodic function, but it's a very specific type. Okay? It is, so let's write, it's a specific cyclical pattern, okay, that follows the curves of y equals sine x and y equals cosine of x. Okay, so it has to be specifically following, and I'll just to kind of give you a hint here, it has to be specifically these smooth curves that go up and down in the exact same manner repetitively. Okay, now I obviously didn't draw it that great, but it would be a smooth curve. So it has to follow y equals sine x and y equals cos x. A cycle, okay, a cycle can be considered a repetitive pattern. These are all terms that I'm going to be using throughout the unit. So a repetitive pattern that starts and stops after reaching the same point. Okay, that starts and stops after reaching the same point. So if you're talking about a, let's see here, a periodic function of some sort, suppose this is my periodic function. It does something like this. My one cycle will be, well, we started at 0, and then for it to come back to 0 before it started to repeat again, this here, okay, this whole thing here would be considered one cycle. Okay, so this whole shape there is considered one cycle. The period gets a little more specific. It is the horizontal distance. So if you hear me say or ask you what the period is of a sinusoidal function or any sort of periodic function, it is the horizontal distance to complete one full cycle. All right, so it's this right here. See that horizontal distance? That is what your period is. So you take one full cycle, which is this shape inside here, and the horizontal distance of that cycle is known as what's called your period. Okay? Next term that we need to know is something called an equation of axes. All right, so suppose we have, this time I'll draw a sine curve as best as I can. All right, and they have to be the exact same curves. Like you can't, I mean, it's hard to draw the exact same curves, but they need to be the exact same curves. Okay, so the equation of axis is a horizontal line through the center of your curve. Through the center of your curve. And so here's what I mean by that. So suppose this curve went from a minimum, let's say it went down to 0 here, okay? And it went to a maximum of 4, okay? Your equation of axis would go right through the middle of this curve at 2. So it goes right through the middle. So you take your vertical distance, so your minimum and your maximum, the distance between your minimum and your maximum, take that, add them together, and divide by 2. Okay, so it's essentially like finding an average, right? So your minimum, let's say you got a 0 on a test and you got a 4 on a test, right? What would your average be? How would you find your average? You would add the 2 marks together and then divide them by 2. And that's what the equation of axis really is. It's an average. It's like your average, and you draw a horizontal line through there. So we say that the formula for it, okay, I'm just going to write it over here. The equation of axis is equal to, you take your y max plus your y min and divide by 2. So in this case, you would take your 0, add it to 4 plus 0, right? Your y minimum plus your y maximum divided by 2. And that's your formula for the equation of axis. Okay, so the location of where to draw it. When you're dealing with these sinusoidal curves, there's something known as amplitude. You may have heard this term before, especially when it comes to music. Okay, and this is what they're talking about when it comes to music. So it is the vertical distance. Because remember I said that sound waves follow a sinusoidal curve. Okay, So it is the vertical distance between the equation of axis, I'll call it EOA, the equation of axis, to the min, the y min, or the y max value. Okay? So here's what I mean by that before I write out what the formula would be. Is if you were to take from your equation of axis and you were to go down to your minimum, that vertical distance right here is known as your amplitude. Also, the exact same value will be going from your equation of axis up to your maximum. This would also be known as your amplitude, and it'll be the exact same value. And so what you need to know is that amplitude is a measurement, and it is always considered positive. Regardless of whether you make your calculation and you end up with a negative value when you do your calculation of what the amplitude is, you need to make it positive, right? Because it's a measurement. It's like saying, you can't, if you're measuring something in inches, you can't say that it's negative inches, right? You're always stating measurements as positive values. So think of the amplitude as a measurement from the equation of axis to your max or your min. And so it's always stated as a positive value. And so here's your formula. Okay, so it is amplitude is equal to, take your y max, and this time subtract your y min and divide by 2. So essentially what you're finding is this distance from here to here, your max minus your min. You're finding that distance from there to there, and then taking that and dividing it by 2. So it's only half of your max minus your min, and that is what's known as your amplitude. So if you're increasing the amplitude in sound, what you're really doing, right, it gets louder, correct? And so what you're doing, if you were to plot the curve of what's happening, is as you're increasing the amplitude, this measurement here is getting larger and larger and larger, okay? Thus increasing the sound. Okay, so we need to remember this formula, and we need to remember this formula. Let's put a box beside them. And then domain and range, I mean, we have done this pretty much in every unit, okay? The domain is the input or the x values within, okay, a given function. And the range is the output or the y values within a given function. And specifically for the range, think of how these are cyclical and they keep rotating from going max to min, max to min, max to min. Knowing your max and min values, that's what's going to give you your range, right? Because it's going from a high number to a low number, then back to the high number, back to the low number, back to the high number, back to the low number. And so your max and min are critical to state the range. Okay, we're going to need to know our maximum and minimum in order to state the range here. Okay, let's start with an example of differentiating between periodic and sinusoidal curves. Okay, then it says state the period, the equation of axis, the amplitude, and the domain and range, okay, of the following. If it's possible, because for some of these it won't be possible. Okay, if it's neither periodic or sinusoidal, you won't be able to find all of these items, right? For example, let's start with the elephant in the room. Is this example here periodic? And if it is periodic, is it sinusoidal specifically? Do you see repeating patterns occurring here with each curve? No, you don't. So this would be neither. Okay? All of these would have to be the exact same size for it to be a repetitive pattern. And the fact is that each of these waves is getting smaller, smaller, and smaller. Okay, so it is not periodic and therefore not sinusoidal. Let's go to this one here, this example. Do you believe that this is periodic, sinusoidal, or neither? Well, ask yourself, do you see a repeating pattern? Yes, right? I do see a repeating pattern. I see one here, 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 and then back down again, right? That's one cycle, right? So if that's one cycle, this is certainly periodic, but is it specifically sinusoidal? Do you see smooth curves going up and down? No. So this is strictly periodic. And this last example here, last but not least, now we see, once again, repeating pattern. So it's definitely periodic, but it's specifically sinusoidal because of the smooth curves. Okay, the smooth curves where the max and the min values are what make this sinusoidal. Okay, so sinusoidal functions are a type of periodic function. Remember that. Okay. All right, now let's do the second part to this. It says, then state the period, equation of axis, amplitude, and the domain and range. Well, we can't do it for this, right? We're not going to do, although we can probably state the equation of axis here, we are not going to do our period, and we can do the domain and range as well, but let's just focus on the two graphs on the left. Okay, so let's start with the equation of axis. Okay, you can just look at this graph and you can determine where the equation of axis is, right? It's right here. It's actually right on what's called the, in this case, it's our t-axis. So t probably represents time of some sort. Okay, so it's right there. What if it's right on the axis? What is the value of it? 0. Okay, so I mean, we could calculate it if we knew what this value was. Like, let's say we knew that this was a 1 and this was a -1. Okay, so the maximum was a 1, the minimum was a -1. We can calculate it, and maybe we'll say that that is the case so that you can actually see how the math works. So remember that the formula is y max plus y min divided by 2. So we're going to get 1 plus -1 divided by 2. 1 plus -1 is 0, and then 0 divided by anything is 0. So my equation of axis there is 0. My period, remember what the term period means. It is the horizontal distance to complete one full cycle. Okay, so hard to tell here, obviously, because we don't have any, we do not have any units here on my x-axis, but it's the horizontal distance. So it would be, let's say, from here to here would be considered one period, right? It's after finishing one full cycle, and then this shape is going to be repeating. You don't have to take it from there. You could even go from max to max. These would be equal, by the way. So this would be considered the period as well as this. It's the horizontal distance there for one cycle. Okay, one cycle. Also, it could also be, I can draw another cycle from here, going all the way up and then coming back down before the shape repeats again. This would also be considered the period. All right, so you can do your period as well from the equation of axis. So you can take your period, you can take the horizontal distance between your minimums or the horizontal distance between your maximums, or you can start at the equation of axis and see how long a cycle takes from there. Okay, so what is our period? It's hard to say because we don't have units here. Okay, but so I'm not going to state them here, and that's fine. Okay, but you can see what it would be. It would be the horizontal distance between your max to max or min to min, or on your equation of axis itself. The domain, pretty straightforward. Okay, what x values can be used within this function? All real numbers. It's going to go on forever in both directions. The range, however, you do use the set of real numbers. However, you're going, what y values do you need to stay within? Your max and your min. So y must be greater than or equal to -1, but also less than or equal to 1. Okay? Let's look at this periodic function here and state the equation of axis. Remember, it's y max plus y min divided by 2. So our max value here is 5. Our min value here is -1 and divide by 2. 5 plus -1 is 5 minus 1 divided by 2 is 2. So our EOA occurs right here through y equals 2. All right, there's your middle, which makes sense. All right, there's like 3 squares above, 3 squares below. That's definitely your middle. Okay. Our period, so now we can actually find the period here because we do have units. So the time it takes to finish one full cycle, well, I would say that one full cycle, let's go from min to min. So from here to here is one full cycle. And how many units is that? Our grid's going by 1, so it starts at 3, and it ends up going to 7. Okay, so that's obviously a total of 4. And I don't know my units, so I'm just going to say period equals 4. Okay. My domain, still XER. Let's assume this goes on forever in both directions. And range is YER, but there's a restriction. We are going from a max y value of 5 to a minimum of -1. So -1 less than equal to y less than equal